Okay guys, this is the first video for the course Chem 550, the Advanced Physical Chemistry course at WKU. I have elected to teach this course as a computational chemistry course. And so it's a little bit different than a traditional lecture-based chemistry course in the sense that there is going to be a lot of hands-on work performing what we call quantum chemistry calculations using a electronic structure software package. And so really it's something in between a lecture and a lab. And so as we go through the course material, I'll be presenting slides and examples illustrating how computational chemistry works. And we'll encounter different concepts that we'll review along the way. As you've seen in my correspondence with you, there won't be any tests in the course. The assignments are all project-based, what I call mini reports. And so you'll have about 2 weeks for each mini report. And so there will be calculations that you need to design and perform, and then you'll prepare a short semi-formal write-up on those calculations. And so we want to make those write-ups as professional as possible. We'll talk about that in more detail in class. For this video here, I wanted to introduce you to the idea of computational chemistry, specifically electronic structure calculations in computational chemistry, what they are, some of the details of how they work, nothing too technical, although you may think it sounds rather technical. There won't really be any equations in this video. I'll save that for a later video if you're interested in it. And so let's get started. So quantum chemistry, what I have here on the slide are 3 points, 3 different general techniques in computational chemistry. And so one type of approach in computational chemistry is called quantum chemistry, which means that the techniques and the methods that are used are derived from the theory of quantum mechanics. These include electronic structure methods that solve the time-independent Schrodinger equation for a molecule where the nuclear positions are fixed. And so here you're focusing on the electrons within a molecule. How are they organized? What are the energies involved? What are the properties of different electronic states? So this is what we mean by electronic structure calculations. How are the electrons arranged? What are the energies involved in that? And then what properties can we derive from the calculated electronic state? And there are a variety of methods for performing electronic structure calculations. One class of electronic structure calculations are called ab initio methods. The term ab initio is Latin. It means essentially from first principles, meaning from the Schrodinger equation. So these methods are derived from physics, and then they are used to calculate the electronic properties of different molecules. That is, properties that are derived from the electronic structure of molecules. In particular, they have some representation, some explicit representation of the quantum mechanical wave function for the mini electron system. So the electron molecules have lots of electrons, and quantum mechanics tells us that there is a wave function that describes those electrons. These ab initio methods attempt to model that mini electron wave function. And there's a whole bunch of acronyms that can be used. So one of them is called Hartree-Fock. Moeller-Plesset theory is another one, and there are other ones as well. And we'll talk about them from time to time, and we'll use them in our calculations. A different approach altogether is called density functional theory. That method, instead of focusing on the multi-electron wave function, it focuses on the molecule's electronic charge density. Okay, and so it's a different approach altogether. It has its advantages and its disadvantages. We'll talk about those in a later video, but these are referred to as DFT methods. And we'll probably be doing mostly DFT calculations because they generally are more economical in terms of giving good accuracy at low computational cost compared to some ab initio methods. Particularly the high accuracy ab initio methods are quite expensive in terms of time and computer power to run. So DFT is a really good approach for doing calculations on a budget, so to speak. Another approach altogether is something called semi-empirical, which is very different from ab initio methods. Semi-empirical methods use parameterized models based upon fitting data to experimental results. And so there is advantages to doing that, particularly if you're interested in very large systems. Semi-empirical methods can be the only method that's available to you. However, they have drawbacks in the sense that you can't easily apply a semi-empirical method to a molecule for which the semi-empirical method has not been previously parameterized. So you can run into trouble if you try to perform a calculation on a molecule that hasn't been included in the semi-empirical method's parameter set. Nevertheless, they certainly have their place. So that's electronic structure calculations. These are what I consider to be the three major types of electronic structure methods. There are more, of course, but those are the three big ones. Now, another topic under the heading of quantum chemistry is called chemical dynamics. And so here, in addition to studying the electrons quantum mechanically, one also models nuclear motion via the time-dependent Schrodinger equation. And so this is a whole nother level of calculations where you're treating not only the electrons, you're treating the nuclei as well. And those are, of course, I find them very interesting. In fact, I have some background in that from my graduate school and postdoctoral days. But we are going to be focusing exclusively on these electronic structure methods. Another heading here, another broad heading under computational chemistry is called molecular mechanics. This is where one uses Newton's equations of motion. So instead of using quantum mechanics, one uses classical mechanics to study how molecules move. And so here the nuclear motion is treated classically using parameterized force fields that represent the electronic structure of the molecule. In a sense, you replace the detailed ab initio calculations with simplified force fields based upon things like the harmonic oscillator model or the Morse oscillator model and van der Waals interactions and things like that. What that does is that you basically eliminated the electronic problem and you're just using classical mechanics to model the nuclei given a particular force field. So this involves a lot of parameterization. Nevertheless, this is still a very important approach in computational chemistry. For example, this is how scientists study very large proteins, because you can't apply these ab initio methods to a large protein structure, or at least not without some finagling. And so these methods are very important in for studying biochemical systems, as well as large polymers and things like that. So we won't really be getting into any calculations involving molecular mechanics, but there's a whole branch of computational chemistry that focuses on developing force fields and developing methods in molecular mechanics that can treat large. There, the idea is to treat very large molecular systems, whereas we're going to be focusing on small to medium-sized systems with our electronic structure calculations. There's other branches of computational chemistry. I've only included one, Monte Carlo methods. These usually follow a different approach. Some of them are quantum mechanical, some of them are classical, but they typically involve stochastic sampling algorithms. So it's just a different brand of computational chemistry that uses very different methods. Okay, well, so for the rest of the video, I'm going to really be having electronic structure methods in mind, and so what I'm presenting on this slide are some of the considerations that one must take into account when trying to model a chemical system using computational chemistry approaches. And so the main rule is that there's always a trade-off between computational cost and accuracy. And what I mean by computational cost are the memory requirements and the time requirements of performing the calculations. So, you have a computer with a given amount of memory and a given CPU speed. It may be a desktop computer, it may be a supercomputer. There is a limitation on the memory and the speed of that machine. And so there will always be a trade-off between the cost of the calculation and the accuracy with which you want to compute your results. So quantum mechanical methods for solving the time-independent Schrodinger equation, or the chemical dynamics methods for solving the time-dependent Schrodinger equation, are very accurate. However, they are completely impractical for large systems because the computational effort scales exponentially with the size of the system. So while you might be able to model a 10-atom system using the most accurate methods available, that's about as far as you can get. That's the cutting edge right now. And that's not very many atoms, as you know. I know that some of your research probably involves molecular systems with huge numbers of atoms. And so there, if you want to make some headway, it just depends upon the system again. There you would probably go for a semi-empirical method, or if you're in biochemistry, you'd probably use a molecular mechanics method. These are inexpensive, but they're not as accurate as the quantum mechanical methods, nor are they as broadly applicable. So for example, if you have a very unique chemical structure within your large molecular assembly, the cutting edge molecular mechanics methods just may not be parameterized for that particular system, and so they're not going to work. Same thing for the semi-empirical. And so there's no guarantee that these calculations are going to work for you. If you really have a unique system, you may have to go to the drawing board and design your own semi-empirical parameter set or your own molecular mechanics force field. And that's no easy task. That should be left to the experts to do. Okay. Another approach, which is kind of interesting, is to combine these two approaches. For example, a hybrid approach where you would use quantum mechanics to study some small portion of your molecular system, and then you'd use molecular mechanics to study the rest of it. So there are methods for combining quantum mechanical and molecular mechanics methods together in the same calculation. And so this can allow you, to study, say, the active site of an enzyme using quantum mechanical methods, and then you would use molecular mechanics to study the broader protein structure as well as the solvent that surrounds it. So that's the idea of a hybrid approach. The method that you choose really depends upon the problem, your desired accuracy. What accuracy do you need? It may be very possible that the accuracy you need exceeds the ability of any method. Okay, which means you have a unique problem worthy of research, in fact. And that's where people who design computational chemistry methods and theoretical methods get excited, is when there's a problem that hasn't been solved yet. The other aspect is the size of the problem that you choose. That's going to determine what method you want to use, as well as what computer resources are available. Now, you can often get access to the very best of computer resources. You may just have to make some inquiries, make some proposals, and you can often, if you have a viable project, you can get computational resources on some of the best supercomputers in the world. So don't let the fact that you don't have a lot of money for computers to slow you down. You can if you run out of resources at your institution, you can normally get some time from a supercomputing site if you have a worthwhile project. Planning and carrying out projects. So there are different aspects to how you design a calculation, and they're all interrelated. So one thing that you need to do is have a clear definition of your problem. And normally what you want to first do is take your big problem, okay, so what is it that I'm trying to do, and you want to break it into smaller ones. And so one way of doing that is to use a model progression. So you might start, so let's take your big problem. Let's say you're interested in some enzyme or something like that, and it has an active site that you know is important. Well, you might start with the active site first, and then you might start modeling that using different approaches. So you would start typically with a low cost, low accuracy method, and then you would gradually increase the accuracy of that method by swapping out for more and more accurate methods that costs more time and computer resources to deal with. So you will often start with a low cost, low accuracy calculation, and then work your way up to a high cost, high accuracy calculation. In the end, it'll save you time if you do that, because you can't, because it's, the calculations don't always work on the first go, and so you don't want to waste time on a calculation that you haven't gotten quite prepared yet using a high cost, high accuracy method. You want to first try to understand your problem as best you can with a low cost method. This is a little bit what I was talking about with the enzyme, the chemical representation progression. So let's say you're interested in that enzyme. You would first start with the active site, and then you would gradually build it up to the full system, and include things like the solvent as well. I guess I have that down here, the environment. Like I said at the top, they're all interrelated. The calculation series progression, that's what do you do? What do you obtain first? And so often what you need to do is to find a good starting geometry for your compound of interest. If a crystal structure is available for your compound, great, you might start with that. If it's a small molecule, you'll just build that you can guess what the geometry should be using elementary chemical theory. Then you can start with that geometry. But sometimes you've got like kind of a unique structure, and you don't know exactly how things should be arranged spatially. You might know how things are connected from your NMR structure, but you don't know how they're arranged in space. And so first you need to determine a suitable or reasonable molecular geometry, and then from there you'll refine that structure and ultimately calculate the electronic structure properties of interest. Things like the dipole moment. You might be interested in the molecular orbitals, you might be interested in the thermochemistry of that compound, all sorts of things that you can calculate using electronic structure calculations. And then how the solvent affects the structure is important as well. So often if you're studying a system in solution, you'll need to include the effects of the solvent because the gas phase chemistry, gas phase structure, the gas phase energies, of molecules are very different compared to their solvated structure. So you'll need some method for including the effects of the surroundings. And that is built into some of these electronic structure packages. Another aspect of performing an electronic structure calculation is you have to choose a model to work with. Okay, and there's all sorts of different models. I mentioned a couple earlier. I talked about Hartree-Fock and the density functional theory calculations and the Moeller-Plesset calculations. These are all different models. Or actually, I should say those are different theoretical methods. Okay, so the method and then the so-called basis set together form the model chemistry. So there's all sorts of different methods out there that you can use. And then, sorry that it keeps jumping around like this on us. The basis set is a component of the model. For electronic structure methods, the basis set refers to a tool, a mathematical tool, that is used to represent the electronic wave function for a molecule. And so in order to mathematically represent the wave function describing a system of many electrons, you need to incorporate known mathematical functions that represent the electronic structure of the molecule. And so these basis sets, they are functions that are designed to look like atomic orbitals. Okay, so think of s orbitals, p orbitals, d orbitals, etc. These have a mathematical description, and that is used within the quantum chemistry calculations to represent the electronic wave function. The method refers to the level of theory that is used to solve the many electron time-independent Schrodinger equation. High accuracy methods that always also are accompanied by a high cost can give you quantitatively accurate results. Your low accuracy, low cost methods, they will give you qualitatively accurate results. So you need to decide what method to use. You always start with the low accuracy methods first, and then you work your way up to the high accuracy methods. So the other feature of the model chemistry is the basis set. As I was saying earlier, these are the mathematical functions that are used to represent the many electron wave function. You are always limited to a finite basis set, so a finite number of functions that are used to represent the many electron wave function. That ultimately ends up restricting the electrons in your calculation to a particular region of space. And so that ultimately limits the accuracy of the method. The more functions you include, okay, so the larger the basis set, the more functions that are in the basis set, the higher the accuracy of the method, but also the higher the cost of the method. If you use a small basis set, you'll wind up with low accuracy, low cost. So there's two components to the model chemistry. Okay, and both of them affect the accuracy and the cost of the method. Okay, so if you use a high accuracy method with a large basis set, that's going to be a very accurate calculation, but it's going to be very expensive to run. Conversely, if you use a low accuracy method with a small basis set or a medium-sized basis set, you're going to wind up with a quick calculation, one that's easy to do in terms of the time it takes, but the results are going to be at best qualitative. Okay, and so, like I was saying earlier, there's always a trade-off. And one of the strategies is to first start with a low accuracy method with a small basis set and then work your way up to a higher accuracy method with the larger basis set. Now, I think the next few slides elaborate on both the theoretical methods and the basis set. And so what's listed here are the so-called Pople criteria. John Pople was a rather famous computational chemist who designed many different electronic structure methods In fact, he shared the Nobel Prize with another computational chemist for his work on developing electronic structure calculations or methods for performing electronic structure calculations. And in one of his papers, he identified the desirable features for a model chemistry. And I just wanted to go through them here because they highlight some of the important aspects of computational chemistry. So the one goal would be to have a method, a model chemistry that is uniform and unbiased, which means that you can essentially apply it to a molecule of any size without worrying about what particular class of compounds it comes from. And so this is kind of the opposite of the semi-empirical or molecular mechanics method, which are parameterized using specific compounds to give a good result. However, you can't use the semi-empirical calculations, or at least not very well, to model compounds that were not included within the training set. Okay. However, certain types of electronic structure calculations are relatively unbiased and can be applied uniformly to any molecule of interest as long as it's not too large of a molecule to overwhelm your computational resources. The one other feature is that the model chemistry should be unique in the sense that it really requires only certain types of information to be supplied as input. For example, what are the positions of the nuclei relative to one another? What is the charge of the molecular species? And then something that we'll talk about later called the spin multiplicity. So that's another input. And so we'll specify what that means as we go. Another desirable feature is that the error should scale proportionally with the size of the system. That is, you don't want the error to get exponentially larger as the system size gets bigger. You want the error to scale linearly with the size of the system. You want your method to be exact in the sense that if you have a very simple system, for example, the hydrogen atom or the helium plus atom, you want that method to exactly predict those results. And so Hartree-Fock methods are exact, that is, they are 100% correct for a simple one electron problem. The idea of having a variational method, it's very useful when computational chemistry methods are variational. That means that the energy that the method calculates, let's say you're calculating the total energy of the molecule, if the method is a variational method, it means that the energy that you've predicted will be an upper bound to the true molecular energy. And the idea there is that if you minimize the calculated energy, then you would have achieved the best possible energy that type of calculation can predict. Right? Because if the energy is always going to be greater than the actual energy, then you can improve upon the result by minimizing the energy in your calculation. Obviously, we want the calculations to be both efficient and accurate. You want to be able to reproduce experimental observations if possible, so that's accuracy. And you need to be able to do that in a reasonable amount of time. It's great if you've got a method that can calculate the energy to perfect accuracy, but if it takes longer than the age of the universe for you to perform the calculation, it's not so useful. One of the points that Pople makes is that there's no one method, no one model chemistry that has all of these criteria met. Okay, so there's always trade-offs in life. The next couple slides talk about the basis set in more detail. So again, these are the mathematical functions that are used to numerically represent many electron wave functions. The more basis functions you have in your basis set, so the more functions you include, the more flexibility you have in representing the many electron wave function, and hence the greater accuracy of your calculations. the basis functions that we're going to be working with, there's different approaches to designing basis sets, but the ones that we're going to be using are atomic type orbitals that are constructed from Gaussian functions. Okay, Gaussian functions have a simple mathematical structure that makes them particularly well suited for numerical calculations. Now, they're not the only type of function that one could use, but they have been shown to be very efficient, and so a lot of types of software out there uses Gaussian functions. Certainly not all, though. There's all sorts of basis sets that people have cooked up for their calculations. We are going to talk about different types of basis sets, and so what basis functions. And so what I've got here are a list of 3 things that you do want to learn a little bit about. And so we'll talk about the idea of a split valence basis set. What this does is it allows your basis functions to change size, and I have included a figure that illustrates that. And so at the top here, we've got 2 p-type basis functions. Okay, and so what split valence means is that you include p orbitals of one size and p orbitals of another size. And between the two, what we're doing is we're taking these 2 waves, right? So the orbitals are wave functions. You're adding them together to create a new wave function. And when you split the valence, that is, if you use p orbitals of different size, it allows you to tune the size of the basis function in your calculations. Okay, so this improves the accuracy. It gives you more flexibility. These coefficients here in front, these represent numbers. So it's a coefficient, a number times that function, plus another number times this function. And by adjusting the values of these coefficients, you can tune the size of the resulting basis function. Okay, so that's what's meant by the term split valence. For example, you might have a carbon atom, with its complete electronic structure. It has filled s orbitals and filled p orbitals. Well, in your calculation, you might want to include 2 sets of p orbitals and 2 sets of s orbitals, or more. You could include 3 sets of p orbitals if you want as well. Including more functions in your calculations allows you to make the calculations more accurate. And that's because when carbon is involved in a molecule, the electrons are distorted. They don't sit in atomic orbitals. They sit in molecular orbitals, as we'll talk about. The next idea about basis functions that we want to talk about is the idea of polarized basis functions. This allows the basis functions to change shape. And so the idea is that you include basis functions with a higher angular momentum. And so here's what I mean by that. So let's suppose we're talking about carbon again. You know that in ground state of carbon, it's just s and p orbitals that are filled. There's no filled d orbitals for carbon. However, if you include in your calculation both p orbitals and d orbitals, what the combination of these 2 orbitals allows you to design wave functions that change in shape. So here notice that they've shown that the function has moved off the center of the nuclei. That is useful when, of course, atoms and molecules form bonds. The electronic charge distribution, let's say, for a given molecular orbital, the molecular orbital is not perfectly centered about the atom, and so it's very useful to allow your basis functions to move around, to change shape, not be restricted to just p orbitals and s orbitals, but you include these unfilled d orbitals to give you more flexibility in the representation of the mini electron wave function. The last one here, you include diffuse functions. Diffuse functions refer to basis sets that have very large s orbitals and very large p orbitals. So for example, if you're representing a hydrogen atom, the hydrogen atom would be represented by a 1s orbital, right? 1s atomic orbital. Well, in computational chemistry calculations, it's useful sometimes to include additional very large s orbitals. That way you can control. It's similar to the idea of split valence, but they're additional orbitals beyond the split valence. These very large s orbitals or very large p orbitals. I think it's usually just s orbitals actually that are done this way. They allow the electrons to be I should say they allow the electronic density to extend far beyond the atomic cores. And so this is useful for systems where you have lone pairs of electrons which expand into space around the molecule, or if you have an anion where there's extra electrons on the molecule that would be further away from the other electrons, or if you have excited electronic states. So for example, when you excite a molecule, the electrons move around to a different distribution, and usually that distribution is more diffuse. That is, it's further away from the nuclear cores, or from where the nuclei are located. Is a better way of saying that. And so, including these diffuse functions makes it easier to represent these types of electronic systems. And so, we typically include these if we can, particularly, and you really need them if you've got an anion or if you're trying to study excited states. They're basically required if you intend to have any accuracy at all. So these pictures sort of represent these different types of basis sets. In computational chemistry or electronic structure calculations, there's a very cryptic notation that is used to represent the basis set. And so here's an example using the so-called Pople notation. So this 6-311G, 311 plus G in parentheses 2dp, this notation actually signifies what basis functions are used. Okay, and so before the dash, this number represents how many Gaussian basis functions are used for representing the core orbitals of the molecule. So for example, if you've got a carbon, the 1s atomic orbitals are called the core orbitals. And so you're representing those with 6 Gaussian functions to represent those 1s orbitals. Then the numbers that are here, sometimes there's 2, sometimes there's 3 digits that are represented. If there's 2 digits represented, this is called a double zeta calculation. And this refers to how the basis function is split. So should I include 2 types of p orbitals, or should I include 3 p orbitals with different sizes? So if you include two p orbitals with different sizes, it's called a double zeta calculation. Zeta refers to the parameter that determines the size of the orbitals. Or if you were to combine 3 types of p orbitals, that would be a triple zeta. Or if you were to do 4, it would be a quadruple zeta, etc. Here, since there's 3 digits, that indicates that this is a triple zeta calculation. And so the valence electrons are represented by 3 basis functions. One of them has 3 Gaussians used to construct it. The other 2 use 1 Gaussian function to construct it. The plus sign here indicates that diffuse functions are included on the heavy atoms. If it was a double plus sign, that would indicate that you would have diffuse functions on both the heavy atoms and on the hydrogen atoms in the molecule. The G stands for Gaussian, I believe. And then this notation here, this refers to the polarization functions that are included. And so the numbers the symbol, the letter and numbers before the comma indicate, in this case, that we have included 2D polarization functions on the heavy atoms, and then the second signifies that we've included additional p polarization functions for the hydrogen atoms. Okay, and so this is where you include these high angular momentum wave functions or basis functions so that it allows the electronic structure to bend and change shape. Okay, that makes the basis set more flexible, and that'll make the calculations you perform with that basis set more accurate. A different type of notation is called the Dunning notation. Here, the CC stands for correlation consistent. We'll talk about electronic correlation later when we go through different methods for calculating the electronic structure of a molecule. Here, the P means that I think it means that the polarization is built into the basis set, so you don't get to choose the polarization functions like we're done here. So you could swap this out with 2dF and include additional F functions in this basis set here. Here the polarization has been tuned, it's been built into the basis set already. Here this refers to a triple zeta valence basis set, and the AUG means that the basis set is augmented with additional diffuse functions. Okay, so there's different types of basis sets have been designed. These are all, I believe, Gaussian based, but there's even more types out there, and they all use a cryptic notation that makes it very hard to understand what it is. Nevertheless, there is usually some type of rationale behind the notation. When you combine the method with the basis set, that defines the model chemistry. And so here's how this slide covers the notation that's used to represent different model chemistries. And so generally speaking, it's a method and then a slash followed by the basis set that's used. In more complex calculations, you might use one method, one model chemistry to determine the geometry of the molecule, and then another method to determine the properties of the molecule. So that's where we have this double slash notation where you would have the method and basis set used to construct, that was used to determine the molecular geometry, and then you might do a very accurate calculation after you've determined that geometry to just calculate the energy. And so you'd specify the energy of it. And so here's two written out examples. In this case, we've used this density functional theory method with this particular basis set to determine the geometry of the molecule, and then the energy of the molecule was determined with this MP4 method and this particular basis set. This is probably a nonsensical approach. I don't know that you would use a DFT calculation followed by an MP calculation. Here, this is something that's a little bit more realistic, where you would use a semi-empirical method, the PM6 method, that we'll probably play around with at some point, to determine the geometry, and then you use the Hartree-Fock method with a 631G basis set to determine the energy of your system. Note that semi-empirical methods don't have a basis set given because they're based on a parameterized model, so there's no basis set there. Here's a different point that I wanted to bring up. It's a little technical, but it's easily understandable. So when you're doing quantum chemistry calculations, particularly electronic structure calculations, inside the computer code, one uses what are called atomic units to do the calculations. And so these are scaled unit systems. They're scaled in such a way that important physical parameters take on the value of 1. So for example, the mass of the electron in the calculation is set to be 1. The charge of an electron, or the elementary charge I should say, takes on the value of 1. Planck's constant here divided by 2 pi. This is called h bar. It's a very common parameter in quantum mechanics. It's assigned the value of 1, but all of these quantities have different values, of course, in the SI unit system. The most important one for us by far is the energy unit that is reported in quantum chemistry calculations. The energy is reported in units of Hartrees, and that can be converted to kilojoules per mole, or you can convert it to electron volts, or you can just convert it to joules if you like. The reason this is done is because these quantities are experimental quantities. That is, someone has to go measure the electron mass and the electron charge and stuff. And so these numbers are actually subject to change. You know, as better experiments come along, we can add more digits, or the digits here at the end might change. And you wouldn't want to have to repeat all of your quantum chemistry calculations over again, just because someone's done a better job at measuring the electron mass. So instead, you use these scaled coordinates. Okay, you do all of your quantum chemistry calculations using atomic units, and then if you need to convert to SI units, you just use the best available numbers to do that conversion. Okay, so that means your quantum chemistry calculations will be as good as they were, no matter how these values improve over time. Next, I want to talk a little bit, and so we're getting close to the end of this video. I just wanted to point out some of the software that we're going to be using. And so we're going to be using an electronic structure software package called Gaussian. In particular, it's Gaussian 16, where 16 refers to the date, the year that this particular version of Gaussian was released. There's versions of Gaussian, I believe, going back to the 60s, if I'm not mistaken, the 1960s. So Gaussian has been around for a long time. Many people have worked on it over the years in both academia, and now it's been a company for a while now. And it's a commercially available software package. They do have academic discounts, but it's also available to, for the private sector as well. And it's able to perform a variety of electronic structure calculations for us. And here I've given you the website to that product. We have it available in the department, so you'll be able to use the software. There is another program called GaussView 6, which is a graphical user interface that assists you in building molecules and setting up the Gaussian calculations. Okay, so that's another piece of software that we're going to be using. There's really two components here. The Gaussian 16 package actually performs the calculations. The GaussView 6 program helps you set them up. Both of these programs are available in the numerical lab on the Macintoshes. GaussView 6 is also available on the Windows computers. However, the Gaussian 16 is not available on the Windows computers. Nevertheless, you can still perform Gaussian calculations from the Windows computers by connecting to a WebMO server that I've set up in the numerical lab. And so this will allow you to use a normal web browser as the graphical user interface for Gaussian 16. It also works with other commercially and publicly available electronic structure software packages. And I wanted to point out that there are many different software packages out there for performing quantum chemistry calculations. And then I've given you a link here which will show you just how many there are. There's quite a few. The reason why we're using Gaussian is because that's what I learned how to use, and that's what I know how to use. I make no claim of superiority or inferiority to any of the packages that you might find out there. Okay. I did want to draw your attention to a couple of websites. Okay, so the first one here, I don't know if you can see this very well on your screens. the Gaussian.com website, which you may find some use in. If you go to the products, you can look up the documentation for Gaussian 16. You may need that from time to time, and so there's information given here about Gaussian. There's going to be more information than you want to read. Let's see. One of these should take us to the documentation. I'm hoping it's this one. Well, this looks mostly like a sales pitch. Anyway, somewhere on this website is, they may have rearranged the documentation on me. But anyway, you can read more about it here. Just wanted to take it back, and then we'll look at it's going to be under support. Sorry. Okay, so if you go to support, then you'll find links to the technical manual for the software, like keyword list, tutorial videos. I'll be making some for you as well. These white papers here talk about doing different types of calculations and more detailed features of these types of calculations, pitfalls, things to watch out for. So that's useful. And then also the user interface has its own website, and so it describes that as well. And then I bet if one of these, perhaps from here you might get, using Gaussian 6, you might get to the to the documentation for that. And I think there's also a help browser within Gaussian 6 where you can learn more about using that program. You may need that from time to time, when you're working on your mini projects on your own. The other thing that I wanted to show you and to tell you was that the notes that I've generated here, as well as many of the example problems that I'm going to be showing you how to set up, come from this book, Exploring Chemistry with Electronic Structure Methods. And so this was written by people that are either employed by or very closely affiliated with Gaussian. I think that they're employed with them. It's the 3rd edition, and so here's the website. This EXP Chem 3. The 3 stands for 3rd edition. There's a lot of good information in here as well, and you may wish to look at that for yourselves. So those are the websites I wanted to show you. The last slide here, just wanted to list, this is essentially the content of the course. So these are the types of calculations that I'm going to be showing you how to perform, and then you'll be doing mini projects for these different types of calculations. And so the first one, the one that will be talked about in the next video, are called single point energy calculations, where you take a given molecular geometry and you calculate the total energy of the molecule. You can also calculate things like the dipole moment of the molecule. You can look at the molecular orbitals for the molecule. There's all sorts of things you can do with the single point energy calculation. We'll also learn how to optimize the geometry of small to medium-sized molecules. We'll learn how to calculate the vibrational frequencies of molecules, which can be used to predict the infrared and Raman vibrational spectra of the molecules. It can also be used to study the thermochemistry of molecules as well. You can predict NMR spectra or analyze different conformational structures. If you think back to your organic chemistry, for example, when you rotate about a single carbon-carbon bond, you get these different conformations and they have different energies. And so you can do that on a large scale. So not just rotating about one bond, but you can analyze all sorts of conformers using this software package. You can model the effects of a solvent using the self-consistent reaction field approach that's built into the package, the software package. And you can do more advanced calculations like scanning the potential energy surface of the molecule, looking at transition states and activation energies, and things like that using the intrinsic reaction coordinates calculations. You can predict information about the excited states of the molecule. So for example, this could be useful for studying the absorption spectrum of a molecule, trying to predict the absorption spectrum and understand the nature of the electronic transition that gives a particular peak in the experimental absorption spectrum. Same thing for fluorescence. And then another type of calculation that we probably won't get to, but we might, it just depends upon your interest and what you want to calculate in your mini projects, so-called onion calculations. These refer to the hybrid calculations that I mentioned earlier, where you combine quantum mechanical methods for some small portion of your system, and then you represent the rest of the system and possibly the solvent if you treat the solvent molecules explicitly using molecular mechanics type of modeling. So these are the types of things that we are going to play around with. This is the fun stuff, not so much the theory and things like that, but what can you do with it? And so we'll explore that as we go throughout the course. And then on the next video, I'll pick up with single point energy calculations, and we'll go through some examples in class. All right, so I'm going to go ahead and stop this video.